Welcome to the online causal inference seminar. Today, we're very excited to have Yiqing Su from Stanford Political Science, who will talk about factorial difference in differences. Talk will be roughly 45 minutes. After that, we're looking forward to a discussion by Erin Hartman from UC Berkeley. Questions today will be handled by Yiqing, so I'll quickly hand over to her.
Thank you, Dominic. So as usual, please submit your questions through the Q&A button at the bottom of the Zoom window. And for today's talk, there will be collaborators, Pengding and Anqi Zhao in our panel list to answer questions throughout the talk. And some of the questions will be saved to the speaker at the very end of this talk. And the final thing to note is that please submit your question as soon as you have them and don't wait for us to stop for questions. And without further ado, please feel free to take over, Yiqing.
We can't hear you right now.
Oh, okay. Can you hear me now?
Yes.
Hi. Hello, everyone. My name is Yiqing from Stanford Political Science. Today, I'm very excited to be able to speak at the online causal inference seminar. And thank you for the organizers, Dominic, Adietaya, and Ying for organizing this seminar. It has become a invaluable resource for the field. I also like to thank Erin, who will discuss this talk despite other responsibilities. This is a collaborative work with Anqi Zhao from Duke Fuqua and Pengding from Berkeley Statistics. This is yet another difference in difference paper, but I hope we can offer something new. All right, so this research is motivated by actually many social science research I've seen, including my own research. 2 years ago, I was working on a paper looking at the effect of social capital on famine relief during China's Great Leaf Famine, which is arguably one of the most deadliest famine in recorded human history. So data structure is something like this. It's a panel data set. We have a cross-sectional measure of social capital. We use a number of genealogy books, like records of family trees. That's a pre-famine cross-sectional measure of social capital. We also have a time dimension. Which we call the social capital baseline factor G, which is time invariant. We also have event time before famine, during famine, post-famine. And then on the right-hand side, you can see a depiction of the raw data by high social capital and low social capital groups. This is the average outcome before, during, and post-famine. We see in both groups, the mortality rate increased dramatically during famine, but increase is smaller in places with higher level of social capital. So in terms of estimation, like many papers we use to fix effects, this is equivalently a difference in difference estimator. We know that there's a big literature on the validity of the problems of two-fix estimator in staggered settings. This is not like that because all counties experience famine at the exact same time. So there's no problem with the forbidden comparison. It's basically a difference in difference estimator. And oftentimes we interpret the coefficient of the interaction term between the baseline factor G and the temporal dummies, indicating the event. So this is from the two-effects of regression depiction of the coefficients of the interaction terms. First of all, we interpret this coefficient descriptively. We basically just say the rise of mortality rates in places with higher level of social capital, according to our measure, is smaller than places with lower level of social capital on average. That's a descriptive statement. We also try to, as social science, establish causal links, right? So we say in the paper that we interpret these differences as the effect of social capital on famine relief. Essentially, we're saying social capital has a causal effect on the causal impact of famine on mortality rate. Okay, in fact, this setting is almost everywhere. Well, it's very, very prevalent in social science, economics, political science, and other disciplines. Here I show you 4 studies. The first one is by one of my colleagues at Stanford Political Science. She is looking at the effect of discrimination against German immigrants during World War I. So the baseline factor is a pre-World War I measure of discrimination at the county level. And then you have this event, World War I. So she's interpreting the interaction term as a causal effect of discrimination. And so the outcome is whether German immigrants use Americanized names for their children. And the second paper is published in AER, is looking at the effect, the moderating effect of religiosity in French departments on the effect of Industrial Revolution. So I can talk more examples, but it's a very common setting in the social sciences. So in this paper, we want to, applied research share a commonality that they all use some kind of two-way fixed estimator or DID estimator, but we argue that it's actually a different research design than the canonical difference in difference design by Carl Kruger in 1994. So we call it factorial difference in differences research design. So here there are two keywords. One is factorial, the other is difference in differences. Factorial designs is a key topic in statistics dated back to Fisher and Yates. And oftentimes people are interested in marginal effect and interaction effects when you have two randomized factors. And in difference is less well known in statistics, but very popular in social sciences, especially economics. It's a Nobel Prize winning idea. It's a research design that allow social scientists like me to estimate the causal effect of some policies using observational data, usually in a panel data setting, sometimes repeated cross-sectional as well. But in this research, we try to bridge these two ideas and use factorial design idea to clarify the settings I just described. Okay, first we clarify the factorial difference in difference as a different research design from a canonical difference in difference research design. By research design, I mean setting, I mean the way that we formulate a problem. It also includes the estimand, the target parameter, the estimator, oftentimes a difference in difference estimator, but you can think about other estimators. Identification assumptions, identification results. This is different from an estimator itself, right? We're using the same estimator, but it's a different identification strategy. So here I show you the classic 2x2 canonical DID framework. We have two groups, but one group is exposed. One group is exposed in red, and then the other group we call the control group is not exposed in the second pair, and we use the difference in difference estimator to estimate the average treatment found or treated. That is what we learned in the first class in causal inference. But in factorial difference in difference differently, both groups are exposed in the second period. So there's no clean control group. Nobody is exposed to the event in the first period, but everybody in the data set is exposed to the treatment in the second period. And that's a difference in setting. But we use the same the difference in difference estimator, and that requires some clarification. So we show in this paper that under canonical assumptions in DID, namely no anticipation parallel trends, the difference in difference estimator captures effect heterogeneity of the event. That's maybe not surprising to you, but we want to be more precise. So here I show you a basic intuition, which is extremely straightforward. If you don't have covariate, you have two pairs, two groups. Use the difference in difference estimator under these two assumptions. Essentially, what you're getting at is a difference between these two differences, which captures effect heterogeneity of event. So that's what difference in the DID estimator gives you. But this is associative. This is not causal, and we need additional analytical tools, namely factorial design, to clarify what we're actually estimating. It's an effect modification, basically, in the stats literature. With covariate, things get more complicated. We need additional assumptions like linearity. And we argued that common two-way fixed estimator needs some modification unless you're willing to impose stronger structural assumptions. We also clarified that if you want to identify G's, the baseline factor's causal effect, like I did in my paper, we actually need stronger assumption than no anticipation and parallel trends. Lastly, we frame canonical DID as a special case of factorial DID with additional exclusion restriction. So basically reconcile these two identification strategies with an additional assumption. There's some related work. We, of course, are not the first to think about this design. In fact, in Professor Cart's 1992 paper before the Cart-Kruger 1994, so he uses a very similar design looking at the effect of federal minimum wage increase across all counties. And the baseline factor includes like youth population, things like that. And in fact, in Angus Pischke's famous textbook, they also talk about this type of design before the canonical DID design and name it or categorize as part of regression DD. There are other papers like that. We, of course, will use the analytical tools in the factorial designs in statistics. And this shares some similarity to Bartik instrument, although we don't have a measure of the treatment. This also has something to do with the an old paper published in 1960s called Lord paradox. If I have time, we'll get into that. Okay, the roadmap for the rest of the talk. I'll talk about the settlement estimate, which I think is the most important, and identification results by graphics, not using much mathematics because of the format. And then if I have time, I'll talk about 1 or 2 extension and come back to the example I showed you earlier. Okay, settlement estimates. So we're going to focus on, for the talk, the simplest 2x2 case. We have 2 groups, 2 periods, and no covariates. You've seen this, this data setting. Every units in the second period are exposed to the event. So we have a study population of n units. The timing of the event is fixed. And then we have 2 periods pre and post. We have baseline factor G equals to 1, G equals to 0. The data, you can think of it as a Y form. We have the G, we have Y pre and the Y post. And then we actually use an additional variable, quote unquote, called Z, which measures the exposure to event in the second period. Note that this Z does not have a subscript T. It's not time varying. It's basically measuring the level of exposure in the second period, in the post period. You may wonder, why do we need this? Because in this data set, it's not a variable. The value of Z is 1, but it's useful analytically, especially in comparison to canonical DID. So Z equals to 1 for everybody. And in canonical DID, in contrast, Z is a deterministic function. Z is basically G. G determines the value of Z. And we use Z because we try to reframe this problem as a factorial design. Okay, so we're working with basically 4 averages, 4 means. Without covariates, we put data into this 2x2 matrix. And we're using the difference in difference estimator, right? Literally, it's the difference between 2 differences. We have before and after difference in G equals to 1 group. We have before and after difference for everybody in the G equals 0 group. And then we take another difference between the 2 averages. That's where the difference in difference estimators' names come from. But for the rest of the talk, I'm going to focus on the probability limit of this DID estimator, tau DID. This is a statistical estimate. It may be causally interpretable, may not be causally interpretable. It can be consistently estimated when we have the IID data by this tau DID hat. But we're going to interpret tau DID with some additional identification assumptions. This is basically these 2 averages of the first difference, before and after difference in respective groups. Okay, so for the potential outcome where we think the innovation of this paper comes from, we frame DID as factorial DID as a factorial design with 2 factors, G and Z. Remember, G is the baseline factor. whose causal effect we may be interested in. Z is the exposure to the event in the second period. So the potential outcome is augmented. Previously, in the canonical DID, you only need one, because G is Z, we only need one potential outcome. But now, one factor. Now we have two factors. So we have four potential outcomes in each period. So for each unit, we have Z, because of the combination of G and Z, both are binary. We have four potential outcomes in the pre-period. We have the four potential outcomes in the second period. Here, for example, Y11 is the potential outcome for unit I in the pre-period when small g equals to 1 and small z equals to 1, when the level of social capital is high, when it is exposed, in the second period, it is exposed to the famine. Okay, so in terms of the observed outcome, we use the indicator function to link this observed outcome YIT with the four potential outcomes. So that's why we need this additional indicator ZI, although there's no variation in the data set. Okay, so now you clearly see the problem. In the data set, actually these red quantities, you never observe them. These four red quantities, you never observe them because ZI equals to 1 for everybody. So you never get to observe the potential outcome when Z equals 0. So we need identification assumptions to help us to circumvent this problem, because the causal parameters will be defined based on at least these four potential outcomes in the second period. All right, so what are the causal quantity of interest? First, in other factorial design, we have the conditional effects. Here at the individual level, we have individual conditional effects. And the first one is the conditional effect of the effect of Z conditional on G equals to small g. We basically fixed this small g value, and then we vary the other. We take a difference between the two potential outcomes. Essentially, it's these two pair of differences. That's the conditional effect of Z conditional on G. Similarly, we have the conditional effect Similarly, we have the conditional effect of G conditional on the value of Z. Okay. So then we also have interaction effects, individual interaction effect for each person, for each county in our data set. We have this differences in the four potential outcomes defined by the minus and plus of these potential outcomes. This is essentially the difference between two individual conditional effects. We call the causal interaction effect. The causal interaction effect can be interpreted as the causal moderation effect. As a causal moderation effect of G or Z, or the causal moderation effect of Z on G, depending on which difference you first take. For example, it can be interpreted as the causal effect of social capital on the impact of famine. Symmetrically, it can also be interpreted as the causal effect of famine on the effect of social capital, depending on your perspective. Although most papers that we look at using the first interpretation because of the asymmetry in the panel setting. Okay, so we're not going to identify the individual effect. We're going to focus on the average causal effect, or average causal moderation of G on Z. That will be our main causal quantity of interest. But oftentimes we also are interested in effect modification, which is not causal, right? It's essentially the difference between two average conditional effects. So here, there is a conditioning on the observed value of G, so while for the causal interaction effect, it's taking expectation over the entire study population. Okay. All right, so next, we want to establish some identification results using mostly graphs. All right, so here I show you a roadmap what we want to achieve in the next 20 minutes. So we have this statistical estimand we call tau DID. It can be consistently estimated by our DID estimator applied to this data. And then we have this associative estimand describing effect heterogeneity. In a statistical literature, we call it effect modification, or tau EM. And then we have two causal estimand. One causal estimand is the causal moderation or causal interaction. The causal effect of G on the impact of Z, or causal impact of Z on the impact of G. And then we also have the ATT, which is a classic estimand in the canonical DID setting. Okay, so what I want to achieve is to establish bridges or links between these four quantities. So first, I'm gonna show you that under canonical DID setting, namely no anticipation of parallel trends, what tau DID gives you, the same DID estimator or two-way fixed estimator gives you, is effect modification. All right, so again, we come back to this 2x2 setting. We have full averages, right? Now here, I only observe Y11 pre and Y11 post, because that's G equals to 1 when it is exposed. Those units are exposed to the event in the second period. Everybody exposed to the fab in the second period. So the second index is always 1. And then for G equals 0, we have 0, 1, 0, 1 in both pre and post. We want to arrive at effect modification by taking advantage of the no anticipation and the parallel trend assumption. So by construction, tau DID is moving this line in parallel upwards, taking into account the intercept. And that's mechanically what the DID estimator is doing. With no anticipation, literally says, no matter what the value, whether you're exposed to the event in second period, in the first period, in the pre-period, the potential outcome 1, 1, and 1, 0 is the same, but it can for everybody, and potential outcome 0, 1, and 0, 0 is the same for everybody. So now we can replace Y11 in the pre-period with Y10, and the Y01 with Y00 using the no anticipation assumption. Okay, we basically do that. We've done that substitution. So next, the reason why we do this is because we want to invoke the parallel trend assumption. Parallel trend assumption is essentially a mean dependence assumption between this baseline factor G and the before and after difference for these two different potential outcomes. Okay, this is to say, so looking at these two parallel red lines, this is to say, for groups G equals to 1, the before and after difference for this potential outcome Y10, when not exposed in the second period, but the value of G is 1, while is parallel to the before and after difference in averages of the Y00. Y00 means when your potential outcome G is the baseline factor is 0, but you also are not exposed in the second period. And that's analogous to the parallel trend assumption in the canonical DID setting. Also, okay, so now with this parallel trend assumption, now we can interpret, as you can see here, we can interpret this tau DID as the difference between these two quantities and these two quantities, which are actually average conditional effects. Because by construction, tau DID makes these two deltas the same. What tau DID gives you is the average between these two quantities, and which is the definition of effect modification. Okay, so now I've first established that we can interpret tau DID as a associative description of effect homogeneity, namely effect modification. Next, I want to establish links between tau effect modification, tau EM, with tau ATT and tau causal moderation. First, before we arrive at tau interaction, tau inter, let's digress a little bit because it's direct. It's very direct, as you will see, to talk about the relationship between factorial difference and the canonical differences. I'm going to show you that with an additional exclusion restriction, tau EM is tau ATT in a canonical DID setting. So how do we reconcile this? Remember this figure I just showed you in factorial DID. The DID estimator gives you, in the probability limit, gives you the difference in two average conditional effects. So now looking at this the difference between two average conditional effects, if this second term is 0, then we basically arrive at a ATT analog for G equals to 1, right? This is basically the effect of Z, the impact of Z for group G equals to 1. This is very similar to the canonical, to ATT in the canonical DID setting. This is where the exclusion restriction comes from. If we believe that for group G equals 0, that y01 and y00 is the same, basically means that they're not impacted. They're exposed to the event, but the effect of the event Z is non-existent for this group of units. You can defend this assumption in classic DID settings, like imagine Kaku 1994, we have a minimum wage increase in New Jersey. You use Pennsylvania as a comparison. If you argue Pennsylvania's wage potential outcomes in terms of the employment were not affected by minimum wage increase in New Jersey, then the exclusion restriction is satisfied. However, you may argue there's a general equilibrium effect or any kind of a spillover or silver violation, then this assumption may not hold. It actually has a very close link to interference and silver violations in the causal inference literature. This also gives us this sense that actually even in canonical DID settings, whether or not the exclusion restriction is satisfied, it actually needs some justification, right? It's not always the case in DID setting. The exclusion restriction is satisfied. So of course, when it's satisfied, this term becomes 0, then the tau EM becomes the ATT analog, even in the factorial DID framing. Okay, so under no anticipation, parallel trend, and exclusion restriction, the DID gives you the ATT, the average treatment effect of the factor Z for the group G equals to 1. Okay, so we established this link. Finally, we want to establish the link between tau EM and tau inter, which is the causal moderation. All right, so we come back to this plot again. So here, I think most people have the intuition that because G is not randomized, tau DID or tau EM does not give you the causal impact of G. But why exactly is that? I need to figure out a way to explain to my colleagues in social sciences why this is the case. Although most people, I will have to say that in the papers that we review, most empirical research realize this problem. They just need additional analytical tools to make it super clear. So imagine there's an unobservable U that determines how units respond to the event. Okay, it's not about G. G actually does not affect how units respond to the event. It's all about U, but U is not observed. U is cross-sectional, U is not observed. And if the value of U is small, then the response is small. If the value of U is high, the response is bigger. But imagine U and the G are correlated, right? And then you observe a bigger response in G equals to 1 group than in G equals 0 group, simply because the value of U are different. That's like the classical confounding, although with the first difference. So that's why if you only look at the difference between two conditional average conditional effect, it's not causal moderation. It's not a causal effect of G on the impact of Z, because G may be confounding. In our example, running example, it may not be the effect of social capital, it may very well be the effect of human capital or the effect of agriculture, crop suitability, things like that, or culture factors. So therefore, tau DID cannot be interpreted as the causal effect of G on the impact of Z, causal moderation. So how can we make this quantity causal? So staring at this tau EM effect of modification, we want to arrive at the right-hand side, which is a difference in the 4 potential outcomes for everybody, and taking expectation over the entire study population. What's the missing link? The missing link, actually, there are a lot of sufficient conditions can make that link. So one we think is more interpretable sufficient condition is this kind of ignorability assumption. The G is orthogonal to the first difference potential outcomes. Here, there are 4 pairs of potential outcomes. So here we are targeting some kind of a ATE version of this causal moderation, like using analogously. If we are targeting some ATT version, the analog of tau interaction, you actually need slightly weaker assumption than this. Just like in the unconfounded literature, we only need a weaker version of the ignorability assumption. But what's different from the ignorability assumption is that we are allowed to take a first difference. That's what the parallel trends assumption biases, right? It only requires the dynamics, the before and after change in the potential outcomes to be independent orthogonal to the assignment of G. It does not require all the potential outcomes, all 8 potential outcomes to be independent of G. That's what parallel trends biases in this panel setting. Okay, so, oh, sorry, I forgot to mention. In the paper, we actually use a weaker assumption, which we call factorial parallel trends, which is a mean independence version. This is independence. We have mean independence version of this assumption, slightly weaker, but I think for intuitive purposes, for applied research like myself to understand what really this takes, and this is actually has a clearer interpretation. All right, lastly, we establish this link. If we have this kind of ignorability assumption on the first difference potential outcome, we can interpret effect modification as a causal interaction effect or causal moderation effect. Okay, so just to summarize, we have the canonical difference in differences where we do not assume that everybody is exposed. Only those who are G equals to 1 are exposed. Then we only need non-anticipation parallel trends, tau DID identified to tau ATT. Now we can reframe canonical DID in the factorial setting where everybody is exposed. We have this universal exposure in our formulation of the problem. Then we need additional exclusion restriction for tau DID hat to identify the ATT. In the factorial design, again, we have universal exposure. The tau DID under non-anticipation parallel trend only gives you effect modification, which is a description of effect heterogeneity. If you have this additional ignorability assumption or some other sufficient conditions that we talked about in the paper, tau DID can identify the causal interaction effect or causal moderation effect. All right, so I don't have time to cover the log paradox. The slides will be uploaded so you can take a look at. It's very interesting intellectual history that has some linkage to our work. So the key message here is that maybe everybody is right, maybe everybody is wrong, because the identification relies on untestable assumption on the structural restrictions on untreated potential outcome. Parallel trends is a type of restriction on untreated potential outcome. With different type of restrictions, you will have different identification results. That's how to resolve the so-called log paradox. But sorry, I don't have time to get into that. In terms of extension, in the paper we explored what about having covariates, what about having multiple periods, but for the sake of time, I only have time to talk about very briefly, not even being precise, the presence of covariates. Okay, so I want to skip the theory when we have conditionally valid assumptions, but I want to start from a perspective of an empirical researcher, right? Researchers like me, in this setting, particular FDID setting, often run two fixed effects regression like this. Okay, so here we have unit and time fixed effects. We have the interaction between baseline factor and the post-event dummy. We interpret the coefficient in front of the interaction as the causal moderation or effect modifications, so to speak. But oftentimes, researchers also include these additional interaction terms, which are baseline covariates, also may be correlated with G, with the time domain. This is oftentimes called the cost race in the empirical literature. In econ or political science, you see a lot of regression like this. Why do we do this? Why do empirical research do this? Because we believe empirical research actually think that the first assumption, conditional on covariates, is more plausible than the unconditional version of the so-called ignorability assumption. That's why they use this functional form, okay? So understanding this, so now we can think about simple improvement to the two fixed effects specification, right? Just inspired by stats literature. A better way to do this is first to demean X for this tau to be interpretable, and also add additional three-way interaction terms, G, X, and post, to allow the relationship between delta Y and X to be different in groups G equals 1, G equals 0. That's like very similar to Ling 2013 paper. Okay, we can also leverage more flexible models or double machine learning models for the relation between delta yi and xi for subgroups gix to 1 and gix to 0. We actually implement this in our soon-to-be a package. So the idea here is really it's really about thinking of the data as a y form data, and we can replace y with delta y, and then we can apply all the toolkit for selection observable designs. We can use stratification, matching, balancing, IPW, dimensioning to make the model more flexible. And here with covariates, with conditionally valid assumptions, what we're trying to say is that within each cell spanned by the covariates, we have a small DID, and that being consistently estimated. Well, of course, also need overlap. So for multiple periods, so previously we only focused on 2 by 2. Multiple periods, there are 2 lessons. One lesson is that just like in other canonical DID setting applications, we can use a pre-period to do a pre-trend test. It's a heuristic test for parallel trend assumption. However, this evidence for the plausibility of the parallel trend assumption is not a direct test. For the plausibility of the parallel trend assumption is not a proof or a support for this ignorability assumption. These are 2 separate things. That needs to be clarified. And we find that sometimes empirical research do not make that distinction. This actually requires stronger assumptions in parallel trend for you to interpret tau DID as causal effect of G. Lesson 2 is that we cannot automatically make the no carryover assumption. In fact, this is like a temporal super violation. In the post period, they're also affected by the event. So you cannot simply dummy out, oftentimes dummy out the event time, because the post event may also be affected. These are the 2 lessons. Okay, come back to the example with the last 2 minutes. So we are looking at the effect of social capital measured by genealogy, which are records of family trees. We're looking at kinship networks, right? The event is famine, 1958 to 1961. Social capital is measured by genealogy. So looking at the famine is in some extreme cases extremely high death rate. Like 16% people in some counties are dead. It's a very deadly famine. It's from official data. We're not exaggerating in a way. So social capital measure is also the geographic spatial distribution. So this is the raw data you've seen in high social capital, high genealogy counties. We have a smaller increase, slightly smaller increase. Actually, in terms of number of people, it's a lot of people. But in terms of proportion, it's not a huge proportion. So we also condition on additional covariates to capture human capital, agriculture conditions, culture, political conditions, things like that. And then these are an array of estimators that we use. The first one is difference in difference, or two-way fixed effect. The second one is two-way fixed effect with the conventional specification, just adding interaction terms with covariates and post-dummy. And this third one is actually our preferred specification with additional three-way interaction. And we also use some machine learning outcome modeling, IPW and IPW, give pretty similar results. We're also interested in the dynamic effects, right? So this is the difference in difference result I mentioned earlier. And this is when we include additional covariates. This is when we include additional three-way interactions. The effect becomes more pronounced. If you look at propensity score, they look pretty balanced. So this is the IPW result. This is the this is the AIPW results. So we can use all the machinery in the cross-sectional unconfounded literature applied to this setting as after we first differentiate the outcome. So you see there's some carryover effects so between the two groups. Okay, so oftentimes we also run into the scenario that the G is continuous or multi-valued. In this case, genealogy books per capita is quite different across the country. It's not only binary. A lot of places have no books. Some places have lower level books, smaller number of books. Some places have a lot of genealogy records. So we basically discretize into three groups, 0 to 1, 2. And what we show here using AIPW is that for places with a few genealogy records, the effect is actually not that much. But the effect is much more salient in places with a lot of kinship networks. This, of course, obviously is consistent with our interpretation of the causal moderation effect of social capital on famine relief. Okay, just to conclude, we formulate Factorial DID as a research design, which is a identification strategy with panel data when there's no clinical control groups. It corresponds to a hypothetical factorial experiment with two factors, the group indicator and then the exposure indicator. We can identify causal effect modification and causal moderation under two sets of assumptions. What to do in practice? We recommend that we first want to assess no anticipation parallel trends, just like in the canonical DID setting by checking pre-trends. It's a heuristic test, but it's very effective. But we also want to justify this ignorability assumption, which is inherently untestable and very strong, and show robustness of findings by conducting sensitivity analysis, right? And if we use two-effects model, it's actually preferable to demean the covariates and then add three-way interaction to make the model more flexible. Of course, you can use more flexible models like AIPW, and we also should not automatically assume no carryover effects. That's all I have today. Thank you.
Thank you for the great talk. At this point, we don't have active questions in the Q&A, but we encourage the audience to submit the questions if you have them, and we'll have more time to discuss them at the end of this seminar. So without further discussion, let's move on to our discussion from Erin Hartman. Please feel free to share your screen.
Thank you. Okay. Make sure everybody can see. Good. Okay. Thank you to the organizers for inviting me, and to Yiqing for a great talk, and to Anqi and Peng as well for the great paper. I've seen a earlier version of this, and it was actually a real joy to get to sit down and read the paper more closely and kind of engage with it more deeply. I will say that I made my slides and I tried to think about what I was trying to take from this paper before I had a chance to look at Yiqing's slides. So I have replicated a lot of his hard and wonderful work. I think you're a great presenter. So see, this is, I think what my goal here was to try and really unpack some of these assumptions and put it in a way that worked for clarifying for my brain. So maybe that's helpful to you all. And if not, I apologize. So just two really quick points, I think, when you read this paper that really come through that maybe we just need reminders of as causal scholars. One is that statistical estimands are not the same thing as causal estimands. And I think as somebody who teaches causal inference, that's, maybe you say like, oh, obviously, or if you just took causal inference, this is obvious to you. But I think what this paper makes clear is that in the literature, when methods get released into the wild, sometimes there's the tendency to think about different questions, or applied researchers have different questions they want to answer, and they're trying to use the tools at hand. And a lot of times this can cause confusion. So that comes across very clearly in this paper, and I think it's a really nice paper for really clarifying what the difference then is between a research design, which is a combination of setting, data setting, assumptions, and estimator, and just a statistical estimation technique. And so what does this paper tell us? I think it's a really clear paper. I think everybody should read it. I think towards the end, I'll talk about some questions about who's the target audience, but I think there's something here for both for methodologists as well as for applied researchers. And it's going to really emphasize this difference between the roles of the identification assumptions or estimation assumptions, how they all get bundled into a research design, and thus how the assumptions we make give us leverage on different quantities we might be interested as applied researchers. And in particular, it's going to clarify when this difference in differences estimator is going to allow us to get at different causal estimands. So they I think, do a really nice job of combining the canonical DID setting, where we have this kind of pure control, and show how that can estimate, how that DID is then equivalent to the ATT. And then we think about this factorial setting, where we have this universal treatment. We think about two different quantities that researchers can get at. Effect modification, or treatment effect heterogeneity, or subgroup effects might be a way that I talk about that with students. And then this causal interaction effect, or causal moderation. These are two very different quantities, and I want to come back to kind of where the paper seems to land on what's of interest to researchers, and what my take on what researchers are really interested in, or at least maybe what's feasible based on the talk. So I think this paper does a nice job of expanding this tool of causal designs And then there's a whole bunch of extensions in the paper that Yiqing referenced, so I won't go into, about how to kind of extend it to the more common estimators themselves. So this is how I would summarize this paper. Again, the idea of a research design. On our far left here, we have different estimands that we might seek. One just might be the statistical estimand, the DID, where we just want to compare what is descriptively, what is the difference in time trends between two groups. For the canonical DID, we get at what's the average treatment effect on the treated. For effect modification, again, this exact same estimator with different assumptions allows us to estimate this effect modification. So what is the difference in the causal effects across subgroups? I kind of think of this as a descriptive causal estimate. Maybe you would take a point with that description. But I think this is a really powerful estimate, which asks is like, we may not know what the effect was, but we know, does it differentially affect these groups? And then the causal interaction effect is going to actually say, what is the causal effect of exposure if we could intervene on this baseline group? And so that's going to be the kind of conceptual distinction between the effect modification and the interaction, is in what scenarios do we think not only could we intervene on treatment, but we could intervene on the baseline group. So I tried to put all this in pictures for myself. So again, Yiqing did a lot of this already, so hopefully this is telling you what you've already heard. So the DID estimator is the statistical estimand. It's just, it's going to estimate this difference in differences. So it'd be the difference between this point here in blue and this black point. That may or may not be of interest. It's going to describe the difference in trends among these two groups. But to layer on and get to the canonical DID setting, we can say this is going to estimate the average treatment effect in the treated. And that's because what we're going to say is there's no anticipation. So our starting points are the same in the groups. And then parallel trends. Here, because of our exclusion restriction, this group is not exposed to treatment. And so this is the trend. You can imagine there's two lines. The treatment and control trends are on top of each other because there's no effect here. And so our parallel trend is actually estimating our counterfactual with no treatment. And under that parallel trends and exclusion restriction assumption, this difference in difference estimator, nothing has changed about the actual point estimate here, right? But our interpretation is now that it's estimating. It's going to be an unbiased estimator for the average treatment effect of the treated. Sorry. Factorial diff and diff then layers on a different assumption. So we remove that exclusion restriction. So to me, like in pictures, what does that mean? If we look at our zero group here, now there could be some effect of treatment because there's universal exposure. So we observe this red line is group zero under treatment. The counterfactual is here under control. We don't observe that. We assume that that's still parallel for our observed group, and we don't observe this gray line either. But now it's very clear that we can't estimate the average treatment effect on the treated. We would need to get the difference between this blue dot and this gray dot. We can't estimate that. What the parallel trends is going to give us is, well, there was some effect for this group zero. There's a different effect for group one, and the diff and diff is estimating the difference in those true treatment effects. So this is where it gives us this, it answers a substantive question, if there was a treatment, what was the difference in those treatments? If there was no treatment or their constant treatment effect, then we wouldn't see a difference there. So we couldn't disentangle those two. And I think that's an interesting point that's maybe worth engaging with in the paper a little bit. But when there's a treatment effect and it's differential across the groups, we could detect it here. And so I would say this is kind of a descriptive causal estimate because, as Yiqing said, it's not the causal effect of the group, but it is a descriptive difference in the effects. So then I tried to think about what is the assumption that we're making for the factorial diff and diff. So these factorial parallel trends, and maybe Yiqing, you can tell me if I have gotten it right. But basically what we have to assume, so this dotted line here is the same set of assumptions we made for the effect modification. But a sufficient condition under this factorial parallel trends assumes that we would also need to assume all of these extra four kind of dashed dot lines, that all of the counterfactuals would have been parallel across groups. So you kind of imagine, I think of this as like a mirror of the trends in group zero and group one. And of course, we only observe one of these four lines in each group. And this is, I would argue, the advantage of drawing it out for myself is that this is an extremely strong assumption. And one that I think I'd like to see the paper engage with more of how we would even begin to justify it. because as you talked about, we can think about parallel trends for effect modification as an observable test, but I really struggle with how we would even begin to get leverage on this assumption. And again, I think the picture for me at least tried to really emphasize that this is a really, really strong structural assumption, or I felt it was. So I want to leave it mostly open to questions from the audience, but just a few questions that I've divided into kind of conceptual ones and ones as an applied researcher. The thing that I guess kind of struggled with is tau interaction really the primary causal effect of interest to applied researchers? And I think in the words you said in the talk and some of the words in the paper, we kind of acknowledge that, applied researchers are acknowledging they can't estimate this causal effect of group. But I'm not sure that that's necessarily what we're interested in. I think to me, it is driven by this idea of like, could we intervene on the baseline group? And a lot of times we don't think we can. And so I don't think it changes the work of the paper. I think as a methodologist, maybe that's the more interesting estimand. But as an applied researcher, I was less convinced that that is the thing that people seek, and that an emphasis more on the effect modification might be enough for me as an applied researcher to just really understand what I can get at, and with, I think, a stronger set of tools for validating it. So maybe that's, I'd be curious your thoughts on it, what y'all think about that. And then again, I found the factorial parallel trends mathematically tractable, but the figure, it took me a little while to kind of really sit down and be like, oh, this is like a really strong structural assumption. And so maybe that would benefit other researchers or the readers as well. I think that the manuscript generally would benefit from a summary table, particularly as you start to map on these extra estimation techniques. It wasn't always clear to me that every, like I could make that table as like the tau had DID, and then it corresponds to all same estimator, different assumptions. Does that also carry through for all of the other estimators, or where are there differences? I thought that would just help me for applied researchers. But I think also where I struggled was what placebo tests should I be running? What are the observable implications I can test? You talked about some for parallel trends again in the effect modification, but it was less clear to me how I would again begin testing this interaction factorial parallel trends assumption. So how would I test those? And then you mentioned sensitivity analyses, but I didn't see them mentioned in the paper. So I'd be really curious. And I was curious how it relates to like some of the sensitivity analyses and say like the BANSAC 2020 paper. And are there ways to get leverage on that? And then I think for just me as a reader, and I think for applied researchers, again, really engaging with the difference between effect modification and the causal interaction effect, and what that would mean for an applied researcher would help. So for each of the examples, I thought it would be beneficial to think about, okay, if we interpret this as effect modification under this set of assumptions, what does that mean? Versus like, if we think of this as causal moderation, what does that mean? And what are the, what does it mean about intervening on these groups in ways that might be different for applied researchers? So I think those are mostly comments for applied readers, but the ones that I think would help the paper really get a lot more leverage. So I'm going to leave it there and turn it over to Yiqing and any questions.
Yeah, thanks for the very nice discussion. So yeah, Yiqing, you have some time to respond if you want. We can't hear you right now. Sorry.
First of all, Erin, thank you so much for the great comments. I only have two very brief points to make. One is whether applied researchers are interested in causal or moderation causal interaction. I think our review of the like a dozen of articles, I think they do, although they acknowledge this assumption. Well, they didn't clarify the assumption, but they acknowledge it can be confounded by other baseline confoundings. But they do try to make the sometimes fairly vague link to the causal argument. Like the one paper that I cited, we cited in the paper, is that they literally talk about the how religiosity hamper economic growth in the title. So that's a causal argument, right? Although in the paper they do make concessions that this assumption is strong, we should interpret with a grain of salt. But as a social scientist, we're tempted to make such causal claims. That's my feeling of reviewing many empirical papers. A second point is the how to evaluate this factorial parallel trend assumption, or what I call the ignorability assumption in the talk. I think we really cannot, just like in other unconfounded setting, right? The only thing we can do is to do some sensitivity analysis or using some placebo outcome that we know the treatment has no effect on. What the parallel trend assumption buys us, we still need parallel trend. The parallel trend assumption buys us is we're allowed to first difference the outcome, right? Then do the whatever we want to do with the sensitivity analysis. I actually have, because we have a minute, the slides, we actually have a sensitivity analysis. Can I find it? Oh, I cannot find the control panel. Here. Okay, maybe not. I don't know how to share anymore. So we do have a sensitivity analysis plot because we use the same machinery, just replace the Y with the delta Y. That's all I have to say. Thank you. Hong, do you have anything to add?
Oh, I don't. Thank you very much, Yiqing and Erin.
Thanks. Awesome. All right, then, yeah, I think it's time to wrap up. First, yeah, thank you so much, Yiqing, for a very interesting talk, and Erin for the nice discussion. So next week we're going to have this will be the last OCIS for this year. We will have Panos Toulis and Wen-Chuan Guo from the University of Chicago. We'll talk about machine learning assisted randomization test for complex treatment effects in A/B experiments. And as a discussant, we're going to have Xinran Li. Looking forward to see you all. I hope you have a great week and see you next time. Thank you.
Thank you all. Thank you so much.